So to quickly go over the warm-up, which for those of you watching the recording, we already went over, so I'm going to go over it quickly. So, logarithms grow the slowest, polynomials are next, exponentials are next, and factorials win, they grow the fastest. And then quick review of the sequences. This first sequence were all the prime numbers. This one, you take each set of digits and multiply to get the next number. So 7 times 7 is 49, 4 times 9 is 36. These are just the first letter of each name of the numbers, and these are each number and its reflection put together. So fun warm-up. So moving into today. Today we're doing more limits of sequences. So at the end of this lesson you'll be able to determine if a sequence converges or diverges. Remember that a sequence converges if the limit exists. Write an expression for the nth term of a sequence. We did this yesterday, right? It's just more of it. And then this is the real new stuff. Determine the monotonocity and boundedness of a sequence. So I know we talked about monotonocity first semester. I don't know if Mr. Thomas and students talked about it. Okay. So I'll teach it to you today. It's easy. All right. These are not really required, but they're very helpful. They're time savers, right? These are time savers. So the first thing that will save you a lot of time throughout this unit is knowing that the limit as n approaches infinity of 1 plus 1 over n to the n is e, right? If you start learning to recognize that, it will save you a lot of time, because if you don't recognize it, it's one of those 1 to the infinity types of limits where you have to take the log of both sides, put the exponent in front, you get a 0 times infinity, write as a quotient, L'Hopital, right? It's quite a lot of work. So if you can just recognize it's e, you are perfectly fine to just write e. Most limits on the AP exam do not have to be justified. You just have to get to the answer. However you get to it is fine. Okay, comparative growth rates. If you have a limit as n approaches infinity of a function that grows faster over a function that grows slower, the limit will approach infinity. And then vice versa. If you have a function that grows slower over a function that grows faster, that limit will approach 0. So without doing any work at all, if I have a limit as n approaches infinity of ln x over 8x squared minus 5, I know that's going to go to 0 because it's a slower over a faster function. If I have a limit of 8 to the x over 100x to the 20th plus 16, it's going to go to infinity because 8 to the x grows faster. Exponentials grow faster than polynomials. So just something to have in your back pocket if it comes in handy. If you forget comparative growth rates, you can always L'Hopital, right? But it's just something handy to help you do limits a little bit faster. All right, everyone have that down? Yes? Okay. Good. All right, so this will be fun. In your groups, I want you to evaluate each of the limits below, find the limits for each of the sequences below, and then decide if the sequence converges or diverges. So take a few minutes, work together, and find the limit of each sequence listed, and then decide if it converges or diverges. So when we talk about limits of sequences, we're talking about the limit as n approaches infinity. Right? There's a lot of, well there's not a lot, but there are several problems that make you really think about that -1 to the n. There is a big difference between adding -1 to the n and multiplying by -1 to the n. So I want you to just discuss. Some of these just require some thinking. Talk about them, think about them. If you're not sure, try plugging in numbers like a billion.
It's either you're adding one or subtracting one. So in this great scheme of infinity, it's like
Really? Does it actually
get rid of it.
just has the same number?
It's just one. Well, it can't just be one. Multiplied by negative. That would be so it is one. It's going to be one or negative one when it's trying to change the sign. Which means that it's going to oscillate back and forth forever. It's going to be negative.
So basically, wait, it's either negative 1 or 1, so it's like so that means
They do.
the limit
He
of
calls
approach
it
is 0.
tic-tac-toe.
I had no idea
I
what
am
they were doing.
so proud of you for making that connection.
I had no idea what that was doing.
That was awesome.
What?
Yeah.
What?
He just figured out that in stand and deliver, they do, the teacher, Mr. Escalante, does a tab method integration by parts problem. And when he does integration by parts, right, and he shows, he's got the table up, the chart, right? So he's got this chart, he puts like the U, the DV, and then he puts like another thing with the signs, right? So he's got whatever, and he goes tic-tac-toe. He always says tic-tac-toe. So, some teachers call it tic-tac-toe. It doesn't really look like tic-tac-toe, but that's what.
So 1 approaches 0. Does that, so basically comes
We tried splitting it up. Wow. It's 1 plus.
You know what you do instead is look at the top and take that n factor square and 1 is the multiply by. Yeah. Yeah, it's easier to break the larger ones.
Infinity minus, just kidding. You get 2 to the end. It's like, after you like cancel them out, you then 2 to the end, and then put infinity. So then that would be.
Think about it.
number 2 also 1.
Divide n minus 2. You can't think of factorials.
Well, I mean, infinity minus infinity over
Yes.
2n. Basically, you cancel infinities out and then you get negative 1 to the infinity.
Bottom, you have n minus 1, n minus 2, so dot. So those all cancel out, like 2n, if n's infinity, you get infinity.
No, negative 1 to the infinity
Okay, I get
would be
it.
1 or negative.
Correct, it flip-flops.
Yeah.
It doesn't approach anything, it literally just flip-flops.
So that means it would approach, so basically, that thing is 1. Because 1 times infinity over infinity. So both first and 1 is 1 and 2
No. Oh, whoa!
It's just unfortunate. Their face is swapped.
Is that a filter?
Give a nice public service announcement for all of them.
Yeah, I'm going to, don't worry. My public service announcement will start in a few minutes or so. Today is February 26th, 2016.
The research page.
Darth Boujley, vlog number 001.
But it has to be
Your face is so they can see you. Oh, bro, don't hit.
You moved the camera, by the way.
I didn't. Did I actually? I can't. Oh, whoops. I'm sorry, guys.
Wind it back.
What?
I was gonna go.
Wait, Kat.
No, no.
Oh, I would have done it.
I'd do it. This problem's very hard.
Alright, so do y'all have answers for all five? Alright, let's talk about these. So for the first one, someone tell me what they think about number one, whether it converges or not, what does it converge to and why? Okay, one student is holding up a finger. I'm thinking it's just the answer, but they're not saying anything, so. Okay, Glenn, yes.
I think it's 1 because the 1 to the negative 1 to the end just ends up being 1 or negative 1, and you disregard it when it goes to infinity.
Perfect, that's beautifully stated. So what happens is, if you have 100 trillion plus 1 over 100 trillion, really, does the 1 really matter, right? No, what if it was minus 1? Does that like massively affect it? No. When you are talking about infinity, and then you add a little constant, it's just completely irrelevant. It doesn't matter if you add it or subtract it. Even if it was a big constant, right? Even if it was infinity and then pretend it wasn't to the end. Just say it was infinity plus 10 million, right? Over infinity, it's still going to go to 1. Eventually, infinity will swallow that constant, and the constant will become irrelevant. So this one goes to 1. So for this one, the negative 1 to the n didn't have any effect. What about for this one? Does this one have, the negative 1 have an effect? Okay, I'm seeing some head nods. Who would like to speak? Yes, Bethany.
So, because when n is odd number, it'll be negative 1, and when n is a even number, it will be positive 1. It's going to oscillate between positive and negative forever, therefore the limit does not exist and it diverges.
That was a beautiful use of the word oscillation too. So, yes, she's absolutely right. What happens is, this limit approaches 1, right? But you're multiplying by negative 1 to the n, which flip-flops or oscillates, right, between negative 1 and 1. So you're going to get something that will always go doo, 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 right? And it will never converge to a single y value. So this one diverges. Hey, could anyone just look at this and write the answer?
Yeah.
Emily, what was the answer? It was E. You are correct. Okay. What about this guy? How do we deal with these funky factorials? Could we break one of them down?
Yeah.
So, how can we break it down?
So the top one, it'll be n times n minus 1, and then if you have n minus 1 factorial on the bottom, you can just cancel those out, and then you get 2 times n.
And then you get 2n. And what is the limit as n approaches infinity of 2n?
Infinity.
Infinity, so this thing diverges. Right? Yeah, whenever you have factorials to deal with, it's easier to break down the bigger one, right? So just write it like with decreasing n's until you hit the smaller one and can cancel them out. Right? Okay, good. Last one, comparative growth rates. So, who wants to talk about comparative growth rates? Someone? Anyone who hasn't spoken yet? So I'm gonna call it. Jinky, how you doing? Good. Which one grows faster, the top or the bottom?
Bottom.
How do you know? What type of function is it?
It's factorial.
It's a factorial, right? And factorials always win. So the bottom grows faster. What does the whole function approach as n approaches infinity?
0.
It approaches 0. Bam. Done. Very good. All right, good. Good. Moving on. Woo, that's big. All right. Finding the nth term of a sequence. So a few little helpful hints for finding the nth term. When we say find the nth term of a sequence, we actually are meaning like write the rule for the sequence. So it says, hey, what's a sub n? And so they give you a bunch of numbers and you have to write what is a sub n. You're writing the rule for the sequence. It's kind of like writing the function, the f of x function, but we're writing a sub n. So, of course you want to look for a pattern. If the terms are fractions, sometimes it's easier to just look at the top numbers and look at the bottom numbers separately. Be careful if the fractions are reduced, that makes it a little trickier, right? For the next ones, I didn't reduce the fractions, I took it easy on it. Most sequences consist of functions that are either linear, polynomial, exponential, or factorial. If the functions are linear, just a quick review on arithmetic sequences, right? So say we have the sequence, let's see, 3, 7, 11, 15, 19, right? This is called an arithmetic sequence because we are adding the same number to get from one term to the next, right? What number are we adding to get from each term to the next? 4, right? Every single time we're adding 4. The number you're adding is the number that goes in front of the n. That's like your slope. Then, the way that I do these is I kind of mentally plug a 1 in and I say, alright, so if I plug in a 1, I get 4. What do I need to add or subtract to that to get to my first term? So I would need to subtract 1. So this is what you're adding to get from one term to the next, and then this is what you need to do in order to, when you plug in n, get that appropriate term. So if I plug in a 1, 4 minus 1 is 3. If I plug in a 2, 8 minus 1 is 7. And you should always, at least mentally, plug a few values of n in and check to make sure it works. Alright, so that's arithmetic. So the common difference, that's your slope. I know, it's weird to think you're adding, that's your multiplier, but it's because you're adding to your y value and your x value is moving over 1 with each plug-in, right? So it becomes your slope. Alright, suppose we have a geometric sequence. So say we start with 3. And we go, let's go 3, how about we do times 4. So 3 times 4 is 12, times 4 is 48. It's 160 plus 32, 192, right? Okay, so now we're not adding to get from one term to the next, we're multiplying to get from one term to the next, right? So if I'm multiplying times 4 every time, then that number, whatever I'm multiplying by, that's the number that's going to go in parentheses and get raised to the nth power. So if I'm truly always multiplying by the same number every time, if it's really a geometric sequence, then what I have to do then is say, all right, well, I need to get to this first term of 3. There's 2 ways to do it. I could either figure out the 0th term and put that in front and keep that n, or I could put the first term in front and do a minus 1. So the reason I need that is because that first term doesn't actually get multiplied by 4, right? So this would be 3 times 4 to the 0 if we plug in a 1. And then the next one would be 3 times 4 to the first, right? And then 3 times 4 to the second. So you can do it either way. So you could divide by 4 and have it 3/4 times 4 to the n, or keep it a 3 and do times 4 to the n minus 1. Let's see, how to recognize factorial. Factorials are easy to recognize because you're multiplying by increasing number each time. So times 1, times 2, times 3, times 4, times 5. That's a factorial, right? So factorials, multiplying by increasing numbers. So, things to just look for. Sometimes there's a decent amount of guess and check involved. So these are kind of fun. It's like a mystery, right? So here we go. So here are 5 fun-filled sequences for you to figure out a rule for. All right, so write an expression for the nth term, or write a rule, a sub n, for each of the following sequences. Work together. See if you can figure them out. Some are easy, some are a little more challenging.
Oh, like that, yeah, yeah. Oh, like that, okay, that's what I meant. I see. 5. Oh, let me go up. Okay. 3, wait. 2, 4. So 1 comes.
Just let me know it's allowed.
2 becomes 8.
Yes.
Oh,
Yeah, as you
five
get
and
each
minus
one, you
2.
should double check with your neighbor. If you're not working them out together, you should at least be using your partner to check.
Number 2, did you get 5 times negative 3 to the n minus 1?
You were, did you get the first one for number 3?
Well, how do you get
4
each
to
one times minus?
plus 5, but then you like starting with 3 or no?
You always, if you're gonna add to go from one term to the next, the number you're adding is the number that goes in front of the n, so it's gonna be a 5n. And then you have to figure out what you have to add or subtract to get that first term.
Got it. Okay, that's easy.
Yeah, good.
For 3, you're adding the one, the previous one.
3 is, what do you think that you're doing?
Adding the previous number multiplied by 2.
It's a good try.
Oh, I know.
You add the first one, you add.
I think I know.
Okay.
Well, 6 times 4. You add 18, and then 18 times.
So you
3 is actually
you do 2 times.
exponential.
So basically, it's like you multiply it by 2, and then you add your number that was 2 places before it. So it's like 4 times 3 would be 8 plus 2. For 10, it'd be 20 plus 8. 28 times practice.
No, it just goes up by 6, 18. It goes up by the number, the increment of 4 times 3.
Oh, so
So if it goes up by 6, it's up by 18, and 4 in the next one, but.
4 times 3. Yeah.
No idea.
Let's see, we know that 3, people are stuck on 3, we know it's not arithmetic, right? You're certainly not adding.
Oh, it's a
You
factorial.
multiply by.
It's not exactly geometric, because you're
No, so
not
the exponent is factorial.
multiplying by the same number every time, right?
Yeah. You
Should I
multiply
ask
by.
But it is an exponential function,
Yeah, I know what it like it goes up by, I don't know how to write it.
3
but
times
it's
2, 3
been
times 3.
shifted a tiny bit. See if you can figure out what type, how, like what is the base of the exponential
3
is,
times 2. 3
and how
times
to
3.
adjust it.
3 times 2. 6.
Let me try a couple and see.
Oh no, 6 times 3.
Let's try
6 times 9. Oh, it's,
doesn't work
okay,
for
basically
any
it's like 6. Which one are you doing?
Yeah,
3.
but you're not super far off.
6
got
to the n minus 1.
It's actually
Try
simpler
that.
than what you have. Yeah.
So you start with 4.
So But you're not multiplying by 6.
Plus 4 plus 6 to the n minus 1.
3 plus 6.
6 to the n minus 1. So this is the first term.
Well, not like 2 and minus.
I got it.
Oh, I know, but I'm done with it.
Oh,
Yeah,
that's too bad.
yeah.
Basically, I have to like multiply by 3, multiply by.
Yes.
Oh, there's to the power of 3 to the power of n. 4 plus 6 to the power of 3 to the power of n.
So you
No.
somehow, whatever you're doing.
Multiplied by 3 to the n.
Which is correct.
Then why wouldn't number 1 be
What?
Wait, what did you say?
For what, number 1? Oh, for 3? 4 plus 6 times 3 to the n. To n minus 1, sorry.
No. Because 1 is 0, 3 is 0, and 1.
You guys get the first one? Everyone good on the first one?
Yeah,
How about
so
the
4 plus
second
6.
one? You all okay?
That would be for any.
So the second one, did you, what about that negative?
Oh, no, I only equals a 1.
It changes sign, right? Whenever something flip-flops sign, what has to be somewhere in the equation? -1 to a power, right? -1 to the n or -1 to the n minus 1, depending. Yeah. So I actually put the -1 in with this one. Sometimes you can, sometimes you can't. You have to have it outside. There will be another one, I think, where it has to be on the outside. But that one, it's okay. Anyone figure out 3? People? Taryn, what'd you get?
I got 4 times 3 to the n minus 1 minus 4 times n minus 1.
Let's see. 4 times 3 to the n minus 1 minus 4 to the n minus 1? 4 times n minus 1. Like that?
Yeah.
Hmm.
I don't know what's the lesson.
Let's see. If I plug in a 2, I get 12 minus 4, which is 8. So it fails for your second term. But it's a good try, and this is actually in the answer. The 3, we know the 3 is in there somewhere, and it is 3 to a power. Because if you think about how to change from one term to the next, so Nikhil, you were the one that was pointing out, like, to go from here to here. So this would be plus 2 times 3, right? And then this one was plus 18, which is the same as 2 times 3 times 3, right? And this is plus, what was this one? 54?
2 times 3 times 3 times
2 times 3 times 3 times 3? Ooh. There's a 3 to the n in there somewhere, right? So, actually the simplest answer for this one, Lindsay, what'd you get?
3 to the n plus 1.
Oh!
It's just the powers of 3 plus 1. I know. So, kind of annoying, a little tricky, takes a little, yeah. So, anyway, sometimes it's just a matter of, well, we know there's a 3 to the n in there somewhere, maybe we need to play with it somehow. Okay, this one's a little bit easier, right? You've got an arithmetic on top and an arithmetic on the bottom. So just treat the top and bottom separately, right? So you just do a sequence for the top and a sequence for the bottom. The top would just be, it would be an n plus 1, right? The bottom would be a 2n minus 1, right? Yep. I don't know why I put the 2n minus 1 in parentheses, but it doesn't have to be in parentheses. It's just there. Just for fun. All right. So did anyone figure out the last one?
At the bottom.
You got the bottom? What's the bottom?
And factorial.
And factorial. The top is a derivation of number 3. Yeah. So the top is 3 to the n minus 1, and then there also has to be what in front of this? A negative 1 to the n, right? Yeah. Yeah, tricky. So, I don't know how like these are going to appear in the future, but I know those powers of 3 powers, just kind of have the powers of 2, 3, 4, simple powers kind of in the back of your mind if you're stuck. Yes?
For 5, couldn't you do negative 3 then? On top?
The problem with negative 3 to the n minus 1 is that if you do negative 3 to an odd power and then subtract 1, you would actually be going in the wrong direction. You'd get like, for negative 3 cubed, you'd have negative 27, so you'd end up with a negative 28 instead of negative 26. So yeah, you gotta have the negative out front on that one. All right, so who can tell me what monotonic means? Anyone remember first semester?
Something with 1.
Something with 1.
Yeah.
One tonic. Right? No one remembers the first semester? Okay. A function that is monotonic means, essentially it means one directional. A function that is monotonic never changes direction. It'll be either essentially always increasing or always decreasing. However, it can flatten. So it doesn't technically mean always increasing. It can be, as long as it doesn't change to decreasing. So what we say is always non-decreasing or always non-increasing. So in other words, if I have the sequence 3, 3, 3, 3, 3, 3, 3, 3, 3, that is monotonic, right? Because it never changes direction. If I have the sequence 3, 3, 3, 3, 3, 4, 5, 6, 7, 8, 9, 10 forever, that's also monotonic because it never switches to decreasing. But if I have 3, 4, 5, 4, 3, that's not monotonic because it changes direction. Do you understand the difference? So you can be, for example, if we talk functions, x cubed flattens out at 0 and then continues, so it's increasing, it flattens, and then it's increasing again. It is monotonic, right? Because it never actually becomes decreasing. All right, so monotonic, a sequence where the terms are always non-decreasing, meaning either flat or increasing, or always non-increasing, meaning it's always the same or decreasing. So this means if we're talking about a sequence, that means that consecutive terms can be equal or always getting bigger, or equal or always getting smaller. All right, now we need to talk about boundedness. Boundedness. Anyone have an idea what it might mean for a function to be bounded above or below? It's pretty much how it sounds. Yeah.
It has a
No.
limit.
Okay, it has boundaries, right? Yeah, it's perfectly good. Yeah, Lauren.
Would that be like a logistic equation?
No.
Where it's like,
Yeah, there's a limiting, a logistic equation is definitely bounded, right? So bounded basically means that there is a y value that it never goes above. That means it's bounded above, it has a top boundary. Bounded below means there's a y value that never goes below. It has a bottom boundary. Does that make sense? So if you're bounded both above and below, like a logistics equation, right, then it has both boundaries. So a sequence is bounded above if all the terms are less than or equal to some number, and it's bounded below if all the terms are greater than or equal to some number. And then a sequence is called bounded if it's bounded both above and below. Then it's a bounded sequence. I don't know why they use m for the upper bound and n for the lower bound. The only way I could think about it in my head was if you list the alphabet vertically, right? Then n is above and n is below, right? So that's how I wrestle with that one in my brain. Not that you would are wrestling with it. It's things I think about. All right, you guys got this? You need another minute to copy if you're copying. Okay, theorem. Any sequence that is both monotonic and bounded will converge. Note, this theorem is not biconditional. That means that the other direction does not work. So, if any sequence converges, that does not necessarily mean that it is bounded and monotonic. All right? So you can certainly have sequences that converge that are unbounded. You can have sequences that converge that are not monotonic. But if the sequence is both monotonic and bounded, it definitely converges. Right? This is a squares rectangles thing. All squares are rectangles. But you can certainly find other rectangles that are not squares. Right? Okay, so, well, oh, I've got the answer up. Wait, don't look, don't look. Go out. Shade. Cover. There. Okay, so, I want you to take a second. By the way, when you're talking about finding bounds, there's a little trick to know. If the function is monotonic, right, then that means that it's always going up or it's always going down, which means the first term has to be an upper or a lower bound, right? Does that make sense? And then the infinity term would have to be the other bound. If you have a sequence that's always increasing, right, then the first term would be your lower bound, and the limit as n approaches infinity would be your upper bound. Because it's always increasing, right? If you have a sequence that's always decreasing, first term is your upper bound, limit as n approaches infinity is your lower bound. The fun you have is when the sequence is not monotonic, determining if it's bounded. And then there's some of those fun think about it's, right? So that's when we get to have some fun with thinking. So for this one, I want you to see if you can determine if the function is monotonic and then determine its boundedness. You can use any method you want to determine if it's monotonic. Sometimes just listing the first, 5 or 6 terms can help you. Especially helps you to determine if it's not monotonic. But you can do it just by looking for patterns. You don't have to prove monotonicity.
One is monotonic but not bounded. But what? I see. Too bad y'all can't see me. You, Tim.
We'll start talking to the camera.
He's been vlogging throughout the class.
Not really. I've been trying to. We'll get to Q&A later.
Like these pulleys a bit.
And mail time.
Go down.
Dude, I'm casing ice.
You'll stand in front of
Next thing I just need is glasses. I'm using his glasses for class on Monday. Hey, y'all want my glasses?
Talking to the camera.
Yeah, I'm tired.
But it's always possible.
Well, I'll become YouTube famous, but no one will see my face.
You should stand up in front of
It is monotonic. Well, I tried to get it. I couldn't figure it out. It could be always positive.
Oh, it's lunchtime.
ESPN top 100.
It's pretty different. I believe that Vince Thomas should be a teacher forever. I have no other I will not be taking questions like this.
here so I don't get fined or shown.
Wait, and then
Basically, the way you make America great, again, is through calculus. Spreading the word of calculus.
So, is it monotonic?
I don't know. Yeah.
Yes.
Are you sure?
Only goes up.
Okay, does anyone want to explain why they think it's monotonic? Yes, Steven.
So the first term would be 1/1, and then after that, the top's always going to be bigger than the bottom, and it's going to keep getting bigger than the bottom because it's being multiplied by 3.
By 3. Beautiful. Exactly right. The top is always getting multiplied by 3. The bottom's always just getting multiplied by 1, right? So what happens is, so the first way that I do it is to just list out the first several terms and realize, look at that the numerator grows by 3, while the denominator grows by 1. So every term, remember that we only are talking about positive integers, right? So every term is going to be greater than the previous term, because top's growing faster. Okay? All right, that's one way to show monotonicity. Another way to determine it, and this is a tricky way, it might come up in the future, but it's not really that important right now, just a little bit, is understanding if you want to set up an inequality. So if I set up the inequality 3n over n plus 2, that's my original sequence, and then I find the next term. So I plug in n plus 1 in for n, and then I solve the inequality. If the inequality is always true, with either a less than or a greater than, if I solve the inequality and the inequality is always true, then I can prove that it's monotonic. The last way to prove monotonicity, which is my go-to, I always start by just listing the terms, right? But if you're unsure, this is my way to go, which is just find the first derivative, make sign line, right? That's how you do it for regular functions. So it's the same for sequences. Just be careful to make sure that you only are thinking about your input being positive integers. Okay? So, yeah. So if the first derivative is always one sign, then the sequence is monotonic. All right, so yes, it's monotonic. Let's talk about bounded then. So since this function is always increasing, that means that your lower bound would be the first term, which is 1. And your upper bound would be the limit as n approaches infinity, which is 3. So, and this function, without, this one is monotonic and it's bounded, it definitely converges. Converges to 3. It's not lunchtime yet, we got 2 minutes. All right, so just for sake of the video, do you want to leave and I'll finish the video?
Yeah.
It's Friday.
It is Friday.
Well, this problem's gonna come back.
Because I don't want to pause it and then restart it, because then I have two separate video files. So, close your eyes for a second. All right, close your eyes, just for a second. All right, so for the video, for the first one, this is not, and if you'll see it automatically just by listing the first few terms, but it does still have an upper and lower, and it does converge. So close your eyes and your ears.
I have my eyes and ears open. I'm not done that. I'm challenged.
There we go.
I've been challenged. Nah, I will stay anonymous.
Okay, so this is a negative to an exponent, which means it's going to bounce, right? So of course it's not monotonic, but it does have an upper and a lower bound. As my students leave, just know that if you draw it out, you get something like this, right? first two terms of the series or sequence. The very last one is easy to see because cosine obviously goes like this. It oscillates, it's not monotonic. Any cosine function is going to have an upper bound of 1 and a lower bound of -1. There we go. So this one, again, I'm not going to mess with it. It's not monotonic, but it does have an upper bound and a lower bound, but it doesn't converge because it oscillates. All right, so there we go. Monotonic means one directional. Bounded means that it has a highest y value and a lowest y value, a y value it can't go above and a y value it can't go below. And it converges, of course, either if both of those are true or if the limit exists. Yay!